My name is Patrick Abbs, and I'm the lead scientist for Cambrya, which is a small research company founded to develop a new kind of neuromorphically compatible algorithm called a density network that we will be overviewing today. The first part of this presentation will go over some core architectural and algorithmic foundations that differentiate density networks from other kinds of algorithms. Then we will see how this is applied in practice by walking through a density network built specifically to perform unsupervised sound source separation. And finally, we will compare density network sound source separation capabilities to other standard approaches on a benchmark test set to see how well all of this actually works. Diving right in, a density network is a new kind of algorithm that operates under neurological and by extension, neuromorphic constraints to perform naturalistic learning. And we are going to unpack the term neuromorphic constraints here a bit. Basically, what this means is that the density network is only allowed to do things that the brain can do. And there are three aspects of this that I particularly want to highlight. First, a density network behaves as a collection of autonomous localized neurons. So neurons can influence each other by sending various kinds of signal, but ultimately each neuron has full autonomy over its own state and behavior. Second, a density network perceives, develops, and acts simultaneously. So instead of having an input that gets processed and turned into an output, or having a training phase and then a testing phase, the network is just in a single continuous state of constant activity. At every moment, every neuron from the perceptual layer onward is deciding what it wants to do, who it wants to talk to. And in aggregate, what this means is that perceiving, learning, recognizing, acting, they're all happening at the same time. And what this produces is learning through unsupervised emergence. So even though the network is a big cacophony of neurons, each doing their own thing, if we set things up right, we should see that larger scale, seemingly coordinated behavior just naturally emerges and gives us something that looks like learning. So what should we get a density network to learn? Well, it would be cool if it could learn stuff that we can learn, since we're giving it similar constraints to our own. It would also be cool if it could learn useful stuff. And it would be really cool if it could learn stuff that other algorithms aren't very good at, since this would demonstrate that all these biological constraints can actually get you something new that standard machine learning can't. So we chose to start with a cocktail party effect, which means separating out a specific sound from all of the other sounds in a noisy environment. And if you've ever been on a Zoom call with someone who's in a crowded coffee shop, you know that this is an unsolved problem for machine learning. But before we jump into the model itself, we're first going to add in a few more constraints, although these ones are not biological. Because we wanted to really differentiate density networks, we decided to take the foundational techniques that have worked well for other algorithms and, for now, toss them out to really drive in that density networks are doing something new rather than just repackaging something known. So one of the major foundations of sound separation approaches is to use several microphones to triangulate where different sounds are coming from. But we gave the density network only one microphone, one ear, so that it can't do this. Another standard technique is to actually train your algorithm before you test it. But to show that density networks have the same one-shot learning capabilities that you and I do, we decided that for every scenario, we will spin up a brand new density network that has never heard anything before and see whether it sinks or swims. And finally, a lot of sound source separation algorithms have to know how many sounds are going to be in an auditory scene ahead of time. So for our network, although it will be consistently trying to follow a musical instrument, each auditory scene will have between 2 and 20 other random sounds mixed in. And the result is a bit like listening to a street performer playing right outside the New York Stock Exchange. And let's take a listen to an example with a clarinet to see what this is like. So this is what our density network is going to be hearing. And one more time for our own benefits. So it's going to be trying to extract out the clarinet here. And if all goes well, what we should get is about a second of kind of noisy audio as the network learns what the clarinet sounds like on the fly, followed by smooth sailing the rest of the way. And there we go. So how does this all work? Let's dive into the model. This particular network has its neurons grouped into 4 different regions closely modeled on the auditory system, with neurons in each region having their own specialized learning rules, signaling behaviors, interconnection structures, etc., although all of them are neuromorphically compatible. First is the cochlear oscillator region, which will turn sounds into signals. Next is the pitch region, which actually will do the separation of different sounds, with a little bit of help from the harmonic region, which will use short-term learning memory to learn what sounds sound like, so it can follow it through the environment. And finally, we have the long-term learning region that develops lasting memories of the different kinds of sounds it hears. And you might notice that there's no output layer in this network. And we will come back to that in a bit, but for now, let's take a look at the oscillator region. This region directly perceives sound from the environment and translates that sound into signals. On the surface, this looks pretty similar to a Fourier transform, that each neuron represents a specific frequency and will produce an amount of signal corresponding to that frequency's amplitude at each moment. However, each neuron is actually a resonant oscillator that vibrates back and forth with its frequency in real time. And doing this not only lets us stick to our neurological constraint of having each neuron function continuously and independently, it also generates signal in real time, which eliminates the several milliseconds of latency that come with a Fourier transform. This is also more computationally efficient, although it would be even more so if we could, say, get a silicon cochlea instead of using our current software simulation of these oscillators. So now that we have a real-time amplitude spectrogram of our street performer auditory scene, let's move on to the pitch region. This region is going to take advantage of a type of pattern that the universe seems to like a lot, called a harmonic series. So every sound that you've ever heard that it has a note or pitch, such as in this case, that clarinet or the telephone ringing in the background, is a harmonic series. And all that this means is that the sound is not just made of one frequency, but rather a bunch of frequencies that are all multiples of the same fundamental frequency. So for example, when the clarinet plays at 100 hertz, it's not actually just producing a 100 hertz frequency, it's also producing 200, 300, 400, etc. So each neuron in the pitch region represents a specific fundamental frequency, like our 100 hertz neuron here. And when we create the network, we pre-wire connections coming in from the oscillator region so that the neuron has connections from and only from all of its harmonic frequencies. And voila, now we have sound separation. When the clarinet plays at 100 hertz, all of that signal from its harmonics floods into this 100 hertz neuron much more strongly than to any other neuron. And then when the telephone later starts ringing at 150 hertz, signal from all of its harmonics will converge onto this neuron over here. But we still have two problems here. First, this sound separation is not going to be very precise. We can already see that some frequencies are harmonics of both the clarinet and the telephone, not to mention the dozen other background sounds that we had mixed in. And so this overlying activation is going to mean that we're going to be getting a lot of background noise flooding in at these shared frequencies. Another problem is that we have no way of actually keeping track of a sound if it changes pitch. When the clarinet moves from playing this note to this note, signal will stop flowing to this neuron and will start flowing to this neuron, but nothing in this region will tell us that this is a continuation of the same sound. So let's see how the harmonic region uses working memory to address both of these problems. Each neuron in this region represents a specific harmonic, and a pitch neuron will forward on whatever signal it's getting from each frequency oscillator neuron to whatever harmonic that frequency corresponds to. So during that first clarinet note, this oscillator neuron from the 100 hertz signal goes through here and over to the first harmonic neuron. Signal from the 200 goes through the second, and etc. And as this is happening, each harmonic neuron is tracking the rate of signal that it's getting over the last few hundred milliseconds or so. And we can see that this forms a stable distribution across the harmonic neurons that represents effectively the average shape of the clarinet's harmonic series over time. In other words, these neurons collectively represent a working memory of what the clarinet looks like. To make use of this working memory, each harmonic neuron projects back its average signal rate not only to the pitch neuron that's forwarding its signal, but to every pitch neuron. And now, when the clarinet changes to a new note and this reroutes signal to a new pitch neuron, the neuron can compare its harmonic distribution across oscillator neurons to the working memory harmonic distribution across the harmonic neurons, and determine that they are similar enough to treat as a continuation of the same underlying sound source. The pitch neuron can also use this working memory distribution to fine-tune its input weights and more precisely extract the sound of the clarinet. The neuron now knows how much of the third harmonic is coming from the clarinet sound, and so even if the telephone in the background shares the same frequency and really drives up the amount of signal coming from here, the neuron can use its knowledge of what the third harmonic distribution should look like to downweight the signal coming into here to get rid of that excess noise. Okay, so now that we've seen how a density network picks out, follows, and hones in on the signals associated with the clarinet, how do we actually translate these signals back into sound? Well, let's take a closer look at this pitch neuron here. We know that at this moment, the neuron represents the clarinet, and that the distribution of weights it's applying to signals across the frequency oscillator neurons represents the short-term memory harmonic distribution across those frequencies. And also, conveniently, each of these oscillators is literally producing a wave at its frequency in real time. So we take each of these oscillators, waves as they're happening, we scale their amplitudes to match the expected harmonic distribution of the instruments, and what we get is literally exactly what we listened to earlier, a reproduction of the sound wave of only the clarinet with every other sound removed. So how do density networks do at sound separation compared to other approaches? To benchmark this, we combine solo instrument audio from a dataset called Good Sounds with other sounds pulled from a Google dataset called FUS that's basically just random scraped YouTube audio. We generated 5,000 of these combinations with tiers of difficulty from 1 to 10, where tier 1 has 2 extra sounds that are a quarter as loud as the instrument, and a tier 10 has 20 extra sounds that are collectively 2.5 times as loud as the instrument. The clarinet one that we were listening to today was a tier 7 difficulty. We compared density, in this first graph, we can see that the density network's rapid self-supervised learning in action. This is the time progression of the audio separation quality score averaged across all 5,000 scenarios. And as we can see, each neuron develops and kicks in, then continues to improve more slowly after that. Over here, we can see the density network compared to 2 prominent unsupervised single channel sound separation approaches, ICA and NMF. And as we can see, other than a blip at the easiest tier for ICA, density networks solidly outperform both approaches the rest of the way up. So to conclude, we believe that density networks are a genuinely new class of algorithm built entirely from a foundation of neurological and neuromorphic principles. They weave together neurological constraints, which are often seen as handicaps for neurologically inspired approaches, to instead turn them into advantages in learning speed, self-supervision, and real-time task complexity. And we are here at NICE because we would love to collaborate with fellow neuro-inspired frontiers people to really bring this kind of approach to its full potential. Things currently on our to-do list include building on neuromorphic hardware instead of our current rough simulation of neuromorphic hardware, more fully developing and integrating long-term memory, expanding into speech, adding new senses, and whatever else you think would be cool to work on together. Our core mission is to be a collaborative research group that uses density networks as a lens to expand how we understand and emulate the brain. And what the specifics of this journey look like is something we would love your input on. Thank you.